There are three same mass objects whose center of mass need to be calculated. For example, if you calculate the coordinate of the center of mass, so the formula is as the masses are same, so mx1 mx2 plus mx3 divided the two by total mass. This is the standard formula. So uh, uh, if you look at this expression, the m cancels out, and the solution is you need to just sum these three coordinates and divide it with 3. So if you just sum these three coordinates divided with 3, sum it, the sum is 6, 9, 12, and if you divide it with 3, the answer is coming 2, 3, 4. So it is B. This question is very simple if someone understand the concept of Coriolis force. Here the velocity is 0, and the formula of Coriolis force is minus 2m omega cross v. So the Coriolis force is 0. The answer is C. This question is very simple. If we took a solid sphere whose axis of rotation passes through its center, its moment of inertia is given by 2 by 5 mr square. But if the axis passes parallelly to this initial axis of rotation that is passing through center, but tangent about this sphere, then this distance is we know this is the radius r. So using the parallel axis theorem, the new moment of inertia about the tangent is the 2 by 5 mr square. We know this is general formula plus m into the distance of this new axis from this old axis, that is mr square of this distance. Then the value becomes 7 by 5 mr square. This is the answer. To do this problem, we need to know two relations between Young's modulus, bulk modulus, and modulus of rigidity and Poisson ratio. Is that y is equals to, or Young's modulus is equal to 3k 1 minus 2 sigma, and another is 2 eta 1 plus sigma. After solving this, we will get 3k 1 minus 2 sigma equals to 2 eta 1 plus. Now another point is k and eta, they both are positive quantities. So now there can be two cases. Either this sigma is positive or sigma can be negative. First case is sigma positive or greater than 0. Then 1 plus sigma is greater than 0. That implies 1 minus 2 sigma is also need to be greater than 0. So First thing is sigma should be greater than, or sorry, from here we conclude that sigma should be less than half if we solve this. Case 2, when sigma is negative. If sigma is negative, then 1 minus 2 sigma, that is the LHS, is always negative. This implies this 1 plus sigma is also negative. So sigma has a lower bound, that is minus 1. So sigma must be greater than minus 1. Hence, the theoretical or the limiting values of Poisson ratio according to the theory is minus 1, less than sigma, less than. And a formula based question. So the depression uh, at the middle is given by W by LQ 4y BDQ. So which is proportional to LQ. So the answer is B. So to solve this problem, we need to understand a concept of bubbles. There is a relation between the pressure difference of a bubble, that is the pressure inside and outside of a bubble, and its surface tension T, and the radius R, or we can say the radius of the bubble. So what is that relation? P I minus PO is equals to 4T upon R. So from here the Pi is given, P0 is given. T is the same for both the bubbles because both are soap bubbles. From that we can calculate this R. We will calculate actually. So then what given? Pi 1 is something 1.01 atm. P inside of second bubble is 1.02 atm. So this is suppose delta P. So R1 is it's to be delta 4T by delta P1. Similarly, R2 is 4T by delta P2. That implies R1 upon R2 is delta P2 by delta P1, which is equals to, again let's write it, R1 upon R2 is equals to delta P2 upon delta P1, which is equals to P inside of 2 minus P0, that is P atmospheric, divided by inside 1 minus P atmospheric. We have seen this. It is given that P1 Pi2 is 1.02 atmosphere pressure is 1 divided by 1.01 minus 1. So R1 upon R2 is 0.02 by 0.01 equals to 2. So if we know Vi and V2 will be the cube or pi upon 3 in the both numerator and denominator. That will be, sorry, yes, that will be this 2 cube. So Vi upon V2 is 8. This is your answer. This is from Kepler's third law. This is a question from Kepler's third law, which says t square is proportional to aq, the semi-major axis. The time period is proportional to square root of the time period is proportional to cube of a semi-major axis. So it is simply t is proportional to 8 to the power 3 by 2. So option T. This is also a very simple problem. It is to answer which statement is wrong. So central force is conservative. We know angular momentum is also conserved in a central force problem because your potential is does not depend on theta or phi. So angular momentum is conserved. Areal velocity is also constant. There is a proof also. But as the potential does not a function of time, potential does not depend on time. There is no explicit dependence of time on the potential, the central force problem, because in central force the potential is a function of the only the radial part. So the mechanical is energy is conserved actually. So this statement is wrong. So this is actually true, but this is not true. So the answer is D. This is also a very direct question. For this we need to remember the gravitational field distribution for a solid sphere. So it is uh, if this is the center, if gravitational field is along this y-axis, and from center it increases linearly from zero, starting from zero. So the question is asked to calculate asked to calculate the magnitude of this field at the center. So the answer is simply zero. This is a formula-based question. To do this, we need to remember the angular frequency of damped oscillator, that is square root of k by m minus b square divided by 4m square. B is the damping constant. Now we can easily calculate this time period t, which is 2 pi upon omega, which is 2 pi divided by square root of k by m minus b square upon 4 m squared, which is equals to, now by looking at the option, we need to take common the square root of k by m from this large square root. Now our square root becomes 1 minus b square by 4m square into m by k. So this cancels out. If you solve this, you can get this expression, which matches with option D. C, sorry, matches with option C. This is also a very easy question. For a conservative system, the generalized force has necessarily the dimension of force? No. Dimensionless? No. Cannot have the dimension of force? May have the dimension of force, so this is also incorrect. May have the dimension of torque, yes. When you when you calculate the generalized force for theta coordinate, your the dimension matches with the torque. This is a formula based question. If you remember the formula for a Hamilton's canonical equation, the answer is very simple. The answer is B. If the Lagrangian is given, then the momentum along x coordinate, that is px, is given by del L by del x dot, which is coming from these two terms. This term half mx dot square minus yx dot. If you calculate it, it is very easy. The derivative is very easy. That is mx dot minus y. This is the answer. Answer is your C. This is also a formula based question. If you take a narrow tube through which a fluid is flowing, the velocity profile of this fluid is given by V is equals to P divided by 4 eta r squared minus x squared, where r is this radius. So from this equation, we can easily see the answer is parabolic. Linear momentum to be conserved, the Lagrangian should be only depend on q dot and t. It should not depend on q. So the answer is C. That is the Lagrangian of a free particle is half mq dot squared. The mass of a relativistic particle is its rest mass divided by 1 minus v square by c square square root. So m0 divided by v is 0.98 c. So it's squared divided by c squared square root. C cancels out. If you solve this, square root 1 minus 0.98 square. If you solve this, it's coming at 5. So the answer is 5 m0. So this is the answer.